Hey guys, this video summarizes a build for an LED light source for fluorescence microscopy. The light source can switch from to 16 different wavelengths all the way from UV to IR, and each LED can be varied in power from zero point 0.1 watts to 3 watts max. It's a pretty nice little light box. I still have to build adapters so I can attach it to microscopes and light guides. I built the box out of plywood, with the circuit diagram etched on the side, and the wavelength selections are through a thumb wheel and a lever that work in combination. The back panel has a DC input socket, a power switch, and the intensity control. To operate, I turn on the power switch at the back, and the selected wavelength of light is emitted. So pretty simple. To switch to another wavelength, I pull the locking lever down and turn the wheel to another wavelength. You can see me here going through a few wavelengths. The 940 nanometer wavelength is not visible to the camera and that therefore appears dark. It does draw current, but I haven't figured out how to see it yet. I started by drawing different concepts and played with like some arrangements, and finally this one seemed to click. So in this one, the 16 LEDs are placed on a wooden disc with holes cut in them for the LED lens. The disc with the LEDs are sandwiched between a knob, a thumb wheel, and a circular heat sink. And this whole sandwich rotates around a bolt, which I've shown in orange in this simple diagram. So the LED wheel would be turned to a specific position, allowing current to flow only through that LED. The first step was to make the disk that would contain the 16 LEDs. I still hadn't acquired a laser cutter, so I did it the old fashioned way. I printed a template on paper and then glued this to an MDF disc that I'd left over from some large holes I'd cut for something else. I carefully drilled holes with a Dremel and then expanded the holes so that the lens of the 3-watt LEDs would fit in. I applied a thin rim of E6000 glue to the edge of the hole and then placed the LED into the hole. Was really careful not to get any of the glue on the lens. Now the rim of the LED around the lens is glued to the MDF surface with the positive with the positive leads pointing to the center. I soldered all the positive leads together to a copper wire and then tested that the LEDs work with my variable constant current supply. I finally got around to getting and setting up a K40 laser cutter. So all the new stuff that I was done on the laser cutter. So I made the turning wheel knob on the laser cutter. This would allow the LEDs to be rotated to a specific LED. I had cut a circular piece of heat sink and glued this to the back of the LEDs with JB Weld epoxy. The heatsink is overkill, a simple thick aluminum disc could have been enough, but mistake on my end. I laser cut the front and back panels and pieces for the locking lever. This lever would hold the LED selection knob in place. I cut these out of 5 millimeter thick plywood. And I'm just showing you the brass bolt and nut that would serve as the axle for the LED sandwich to rotate. And also it would be the electrical connection for the positive end of the LEDs. I printed a label for the LED selection knob on an inkjet, and then this was glued on with the numbers displaced by 90 degrees, so that the number on the right will actually indicate the LED that is sitting on the top. This was obviously sealed with acrylic varnish. And for the back panel, which I'm showing now, it actually made a few mistakes in the design. So I had to create a plastic etch label for the variable power switch, plus that extra hole that you see in the middle, that will be covered with a piece of wood. The spring-loaded ratchet was attached to the inside of the front panel. The spring-loaded lever pivots around a screw, and this holds the selection knob in place. The front panel was made from a failed attempt at an astrolabe, therefore the weird designs on the wooden plywood. And now I test fitted the brass ball to make sure it kind of fits okay. The front view of this panel shows the head of that brass bolt, and the screw with the damaged head is the pivot for the lever. I then slipped a sandwich of the LEDs onto the brass bolt and then soldered the common positive leads, the copper wire that was connected to the positive leads, to the washer. And this would form essentially one end of the switch, this large switch, in which the LEDs would rotate. I had put small brass screws into the MDF disc that actually contained the LED lens, and then each screw was soldered to the negative lead of the corresponding LED, the closest LED. So finally, 16 screws, 16 solder joints for 16 LEDs. As the disc rotates, the brass screw head makes contact with the bronze strip. This bronze strip was from an old Kodak Brownie camera, so I guess repurpose really old technology with the new. And now this bronze contact would form a negative contact for each LED as it rotated to that to the bronze contact area. And that spring-loaded stop locks the LED wheel after each rotation. Next is to build the electronics that I've shown in this diagram kind of very crudely. I use the LM317 power supply chip as a defined current source. It's really well explained in this diagram from bristolwatch.com. And the values of R3 that determine the current output is shown in this table that I calculated in Excel. I'd also calculated the waste heat that would be generated by the LM317, and this increases with increasing DC input supply. So at 19 volts DC input, which is what a laptop typically supplies, I would need a heat sink to hold to kind of manage around 5 watts of heat power. The electrics are shown in this diagram. A 9 to 19 volt power supply feeds the LM317 constant current generator, with the constant current being determined by the bank of resistors. The output of the constant current generator is fed to the common positive LED lead, which is now the brass bolt, and the negative would be supplied to the bronze junction with the LED. So that's how I would complete the circuit. And that diode you see in there is just make sure that the power supply is not reversed. It would damage the electronics downstream. I cut out the remaining panels from 3 mm. I then attached the switches, the heat sink for the LM317. It's again a bit overrated, but that's what I had in hand. The DC power socket and the LM317 to the back of the panel. The output of the LM317 goes to the small brass kind of springy thing, which I had removed from a British AC power socket. This brass socket will wrap around the brass bolt and it will complete the circuit. So the brass bolt can rotate within the socket without breaking the circuit. The resistor was soldered directly on the rotary switch with plastic tape serving as insulation. Finally, I tied everything together, put on the final panels with edge gluing, and for the last panel, I had painted it first and then etched it on the laser cutter. This looks pretty good. Being anal here, but checking that all the wiring is good from the power jack to the diode to the LM317 to that brass compression clip and to one of the common terminals on the switch, and finally to the LED selection knob slider. Sorry, the black wire that connects to the LED selection knob slider. Okay, time to do a test run. Connected the brass clip, the positive supply to the brass bolt, and then tested the if the LEDs lit up. The 850 nanometer LEDs do change in brightness when the variable current switches change. So relief, the thing works. So finally, ended up getting a nice little variable wavelength, variable power LED source. Still have to make the adapters to attach to the microscopes and the